She was like, no, she was using it. This morning I was like, oh, these are my grades.
Just put them back.
She wasn't mad.
Yeah.
Yeah,
Well, it's funny because I was making my grades from the sheet.
yeah, that's what she said.
All right, it's 12:30 sharp, and every minute is important here because especially as I'm trying to cover introductory topics that I did not cover last year, means we're going to be behind where I would like to be this semester, maybe by 6, 7, 8 lectures. Okay, so I'm going slow now. That won't be the case all the time. Okay, so I'm trying to educate you with things that some may have not seen before. And actually, some we may not even use them exactly as they are this semester, but certainly you're not going to bring introductory topics on a later course, right? This is the time to do those things, and I want to be sure that we cover them. So the website has been updated, sort of. It has the video lecture that it was messed, okay? It always happens at the start of the semester. It has at least the office hours, on Mondays for the TAs and mine. So we will start having office hours from tomorrow. And we're going to be posting a homework, I think tomorrow, but the homework may contain problems that in areas that we have not covered yet. So whatever day it says is due that day, interpret that is due after we cover the last topic needed in the homework. Okay, and I will give you a warning what that is going to happen. So it will be at least 2 weeks from now, but if it is 2.5 weeks or 3 weeks, we will decide as we go along. All right, and so I don't forget, I did a count on the lectures that I will be missing because of travels, and I realized the Friday lectures are only 50 minutes, so we have no choice, but for me, unfortunately, to teach tomorrow. So please come. Okay, it will be just, I think the timing is a little bit different if I remember, it's like 11:30. Okay, so there will be a lecture tomorrow. Okay, so let's go back to continue where we stopped. So let me give you a rapid review of what we were discussing. So really, we're talking about events, okay? And in this particular case, we consider the events, the joint event of two events x and y, taking the discrete values xi and yj, and we define what's called the joint probability of x and y. Okay, so I remind you the schematic here. If we do, let's say, n experiments, and x takes the value xi and y the value yj at the same time, and this number is nij, then this joint probability is nij divided by n. And I also remind you that Ci is the number of times that the variable x will take the value xi. So that's the marginal. We don't look at what y does. So in n times, x takes the value xi, Ci times. All right, and this are the extreme two fundamental rules in probability, rather trivial. What you see them here is in terms of events and probability of events, but obviously, we will extrapolate this to probability density functions and the like. So if you already have taken a course in probability, don't bother about the concept event, random variables. The same equations are applicable. Okay? So the sum rule is basically marginalization. If you have the probability of x and y, and you want the marginal, effectively you have to integrate out for all possible values of y. So in a continuous space, you can think of this being an integral in y. So sum rule or marginalization is what you see here. And then we define the product rule by writing the joint probability distribution of x and y as the condition of y given x times the marginal of x. And you can also write it the other way around, the conditional of x given y times p of y. Okay? And we effectively gave sort of a proof for these discrete events just looking at that picture. There was nothing major there. Now, I promise you we're going to be spending many lectures and we're going to see Bayes' rule infinite times. So I wanted to throw the Bayes formula now because really it's there. All right, so we don't need to wait 10 lectures to see Bayes' rule, but if you think this is it and we're done, you are in the wrong class, okay? We will play with this equation practically in every lecture from, from now on. So the idea here is, if you want to find the conditional of x given y, somehow with the combinations of the sum and the product rule, we can compute this using the conditional of y given x and the prior of x, and then on the denominator we had the marginalization that also comes from the sum and product rule. So if you have any questions about this equation, please come to see me. Send me emails with whatever questions you have, all right? Obviously here I put x prime to indicate, because I'm summing up, right? The little x and little y are fixed because this is the left-hand side. So this is a marginalization. There is no x here, so I'm introducing a dummy x prime, and then I'm going to integrate for all x prime values. Okay? So this is literally the Bayes rule, and exactly how it's going to be used is going to be the subject of this course. For now, treat this as an exercise in manipulating probabilities. Okay? Nothing basically fancy about that. And again, we will see later on, right, that the same formula can be used to define what's called generative classifiers. So if you have data coming from, from different classes, from different Gaussians in a mixture, or if you, have different labels and you want to find a given data point x to what label it belongs, it's basically, again, an application of this Bayes formula. And this is called generative because effectively it requires that for each label, you need to know how the data are generated. You need to know the probability of x for each label C, okay? These theta here are just parameters that are required to define the two distributions on the numerator. Again, the same equation, it's just different symbols, but has completely different meaning in a different subject in the context of what's called generative classifiers. All right, so let's go now slowly and discuss again a little bit about the independence of two events. So we define the independence of two events, and we write that A is orthogonal to B. We want the probability of A and B. Or you can write this PA comma B, it's the same, is P of A times P of B. And if you use the definition of the conditional that we had before, and this definition of independence, right, you can show actually in half a line that the definition that we use up there can be written in another alternative form, exactly the same equation more or less, that says that the probability of A given B is the probability of A. And this is easier to understand. The idea here is, if you know B, it doesn't help you to say something about A, so the probability of A given B is really equal to P of A, okay? So this equation and that equation are equivalent. One leads to another. Now, almost everything in statistics is going to be conditional on something, okay? And a lot of students get sort of headaches, with the many arguments that we condition probabilities. The only thing I want you to know is, right, you can, if you condition on Z, right, think that Z is not there for now, right? This equation looks exactly like the equation we had up there, that X is independent of Y, okay? Now, if we make everything conditional on Z and you put Z there, then you get what is called a conditional independence relation, right? So the idea here is X, Y are independent given Z. This is very important because, for example, in many occasions, if you don't know Z, X and Y are not independent. Okay? So given Z, we say that X and Y are independent. Okay? This is the conditional independence relation. For good or bad reasons, we're not going to be pushing these concepts extensively in this particular course, but if you take a course on network theory and probabilistic graphical models, almost everything there is based on understanding these relations very well. Okay, so this is a good time to throw these ideas there. I explained to you, and I don't know if you guys took the time to read this example, that when you have a bunch of events, even if they're mutually independent, so if x1 is independent of x2, x1 independent of x3, x2 independent of x3, all three together, they may not be independent. Okay, so don't bother to check mutual independence and then happily say, oh, so x1, x2, x3 have to be independent, because they are not. Okay, and I don't want to go through the details. You should read it. It's a trivial example. All right. It works on a sample space 1, 2, 3, and 4, and x1, x2, x3 is that the ball drawn is 1 or 2, 2 or 3, or 1 and 3, and easily you can see all the calculations here to convince yourselves that pairwise independence does not imply mutual independence of x1, x2, and x3. I think that's where we stop more or less there on Tuesday. So I want to do another example that, again, has no significance really for this course, but for probabilistic graphical models, it may be sort of one of the starting slides for discussing causal reasoning. So it may have implications in your work. So let me just throw it there. So what I have is I have three events, A, B, and C. Okay, and I am using a notation that you will learn later on, so at this point may not have significance, but I can think of C as being the father of A and B, okay, or the parent of A and B. And what does that mean? So let me read the events. The event C is that it's raining today, okay? A is that it will rain tomorrow, and B is that the ground is wet today. Now, you can appreciate the fact, right, that if it is raining today, this immediately tells you that it may rain tomorrow or that the ground is wet today. It explains those events. Okay? So the fact that I have C, all right, explains A and B in a way that knowing B will not add any information about A if I know C. Because C already explains A and B. And what that means is the following, that conditionally on C, and that's why you see here dark circle, that means that C is known. So if conditional on C, A and B are independent. Okay? And more generally, observing a root node or a parent separates the children. And there are many of these relations that we will learn in, if you take this probabilistic graphical models course later on. But some of you who work on causal reasoning, this type of ideas of independence are extremely important, and they come with a nice graphical interpretation to do this type of manipulation, so you don't have to worry about the algebra. Okay? So again, in this case, knowing C, all right, makes A and B independent. And again, if you try to take this definition of conditional independence and you try to prove if marginally A and B are independent, you will realize they are not. Only conditional on C. Okay? All right. We discussed this example on Tuesday. So I'm going to give you two slides that they're sort of a little bit more advanced than what you expect on a second lecture, but I know you can take it, okay? And again, I am not going to use those this semester at all, but this is a good time to bring them in, okay? So let me discuss this, what's called the conditional independence theorem. So let's say that x and y are independent given z. So the theorem says that the conditional probability of x and y given z, it's written equal to some function of x and z times some function of y and z for all y, x, y, and z such that p of z greater than 0. Okay? So let's not bother about this for now, but effectively this conditional independence says that this probability is written as a product of some function of x and z, function of x and z, and some function of y and z. So let me highlight the proof. I like putting proofs in the slides, right? Because if everything is a blah blah statement, if I only give you this, it will not make a lot of sense. But if you actually bother to look through the proof, you realize that this statement is actually trivial. There's no deep knowledge there. It's a very trivial statement, but has implications in calculations and simplifying things in complex systems. So let me try to decode what this statement says. So let's assume, so we want to prove that the left-hand side leads to the right-hand side and the right-hand side to the left. So what I'm going to do is I'm going to start assuming that x and y are conditionally independent given z, and I'm going to show that from this independence we can get this factorization. Will you agree with me that by definition conditional independence means this equation here? Right? So I call this function, it's a function has arguments x and z, and this is y, z, done. So that's, you know, in certain ways that's obvious, right? I just use the definition of conditional independence, and I call this my function g of x and z. There's no y here, there's no x here, so there's another function of y and z, and the theorem's done. So we're going to go now backwards. We're going to assume a factorization like this, and we're going to assume actually, and we're going to prove that x and y are conditionally independent given z. So this is a good exercise in manipulating, using the sum and product rules, right? So there is merit to actually see and do this calculation somehow by hand. So the first thing I'm going to do is the following. So we assume this factorization. So what I'm going to do is I am going to sum both sides, left and right, for all possible values of x and y. So when I do this on the left-hand side, I'm going to get 1. Why is that? So I'm going to sum left and right side of this equation that I start with. And the first thing I notice is, if I sum in x and y, I get 1 here. Why is that? Because this is probability, so you know it is normalized, right? If you sum for all possible values, all the sum of all probabilities will give you 1, okay? All right, that's 1. I'm going to sum in x and y, okay? I substitute the conditional with these two functions. You notice the argument that involves x is separate from the argument that involves y. So basically from this I can show that this summation of the g's for all x's and the summations of the h's for all y's, it's equal to 1. Okay, and I call this equation 1. Now let me compute the conditional, so p of x given z and p of y given z. How do you get, if you know this, right, you have this factorization and somebody tells you, I want the marginal of p of x given z. How do you compute marginals? What's the rule of probability that allows you to compute marginals? How do you go from joint distributions to marginals? Sum rule. And it doesn't matter that this is conditional on z, right? So the sum rule says, to find the probability of x given z, I'm going to sum on y, all right? So this is my expression, and I'm going to sum on y. So there's no y here. I have g of x and z, and summation on y. So I get this nice term here. And I'm doing the same thing to get the marginal of y given z. There will be a summation in x that looks like that. We're done. If we take these two conditionals, we multiply them, we're going to get g of x and z, h of y and z, and the product of these summations, and this product of two summations is equal to 1. So basically what we get is g times h, but g times h is the joint conditional, so we prove what we want to prove. Okay? This is extremely important, right? Because if you have many variables x and many variables y, and they're conditional, independent, somehow you can factorize this very high dimension distribution in terms of this local potentials for distribution. So this sort of is going to be an important type of calculation in addressing the Gaussian dimensionality by taking advantage of conditional independence relations. For now, since I am not really going to use this, consider this as an exercise of the sum and product rules, okay? and nothing else. But somehow this equation, it's very appealing visually. I mean, it makes sense, right? Okay. I have 3 homework exercises in playing with these conditional independence relations. So I'm going to do one of these exercises, and you guys look at the notes and you do the other 2. Okay? Not all of these equations that I have in this sort of homework problems are necessarily obvious. So let me do the first one, the easiest one. Given z, if x is independent of y and w, then x is independent of y given z. So basically what you see on the right-hand side, I put a statement on the conditional independence of x and y, and I have completely removed w out. Now you may say that's obvious, right? If x is independent of y and w given z, obviously it's independent of y given z. Well, I don't know if it is obvious to you. Is it? It is? All right, so let's formally see why you should do these exercises, because you can learn from this product and sum rule. So we start with the left-hand side, and we use the definition. What's conditional independence means? That the join of x, y, and w given z is written as the product of x, the probability of x given z, times the probability of y and w given z. We agree that that's the definition? Right? That's the definition, nothing else there. Okay? So now what I'm going to do is I'm going to get rid of w, because you notice on the right-hand side there is no w. So how do I get rid of w in this equation? I am going to integrate out w. I'm going to marginalize. So I integrate this. Will you agree that if I get rid of w, I get this on the left-hand side? And then on the right-hand side, I'm going to have summation for all possible w's. Okay? So again, this equal to this has no w in it. And here I have this for all w's. So what will this summation give me? Will give me the probability of y given z, right? That's again the sum rule. So effectively what I have proved now, that x and y are independent condition on z, okay, which is what we want.
So the lowercase w is just for all w's?
So yes, so basically the notation, I remind you, the capitals are random variables, right, or events. The little letters are the values they take, okay? I mean, you can abuse the notation and put there big W. Nobody will complain, but it's a good idea to sort of be a little bit rigorous, okay? You should be picking up these things, as we go, because when you write papers, somebody may come to you and say, your notation is not, I don't know how you learn your statistics. And then my name will come across and will say, this guy doesn't know anything, he's an engineer, okay? All right, there are 2 more exercises that I want you to do them. They are simple applications of the rules of sum and product, so I'm going to leave them for you, okay? So I'm going to bypass them. Okay, so let's formally now, without really any deep mathematics, start introducing this concept of random variables. So what I'm going to do is I'm going to assume that I have some probability measure for events, okay? So basically I have a way to assign probabilities of different events, and I have the sample space omega that is the space that contains all possible events. All right, so what is a random variable? And a real value random variable is nothing else but a function from the sample space to real line. So basically is a function that takes an event, right, that you roll heads, for example, that's an event, and it gives you a number, and the number can be 1/2, some number, all right? So a real value function, random variable x, is a mapping from the sample space to the real line. Okay, so x is the random variable, omega is an event, and you notice here it says little omega belongs to the sample space. That's the space where all the events are coming from, and little x is a real number. So a function that takes an event and gives you a real number. Okay? I mean, I'm sure you have used this and abused it, you know, as an undergraduate, maybe without any deep meaning, but there's really sort of, you know, this thing tells you what we want to know, okay? You take an event, somehow there is a function there, and it gives you back a number in the real line. All right, so now that we have a random variable, we need to define the probability distribution of the random variable x. And the only thing we know is the probability of events, right? This is how we started. We know something about the probability of events, but now we want to find the probability distribution of x. So we're going to define this as follows, okay? So pay attention, because again, the notation, I don't want us to be, to get headaches with the notation. So let's take a subset of the real line, right? Because the function is defined, it gives us values everywhere in the real line. So we take, you know, a subset of the real line, let's say 0 to 1, and we're asking, what's the probability that will be from 0 to 1? And here is the way we define this probability distribution of x. We say that this probability is equal to the probability of all the events, omega, that through the function x are mapped to the domain B. Don't lose me there, all right? The only thing we know is the probability of events, all right? And to define the probability of the probability distribution of capital X, Px for some subdomain of the real line B, what I do is I take all the events that through the function x are mapped to B, because you remember the function maps things to the real line, and that probability that I will calculate is the probability distribution of x. I mean, we need to define the probability of x through events, because this is where we started with, okay? So I am looking, find all omegas that are mapped to B, and then that probability will be Px of B, and I call that the probability distribution of x. All right? Confusing? Okay. The answer is yes, but you will read it again and again, and so you have some sense of what this means, because I do know that you use it without really worrying about what its meaning is, okay? So usually this probability distribution of the random variable x is calculated through what is called a probability density, and effectively the probability density is defined through this equation that you see here. So effectively, if you want to find the probability distribution of x for the domain B, is integrating what we call the probability density over the domain B. Okay? So I'm sure you have seen this, right, and play with this, but obviously to be able to define the probability density with this equation, you need to have this definition first, otherwise the whole thing doesn't make sense. All right, and when you have many random variables, right, and you write products, this is really the correct notation. So, you know, P of little x, because little x again are the values in real line, and you put a subscript, the random variable capital X. But lots of times, again, when you write simply P of x, the notation sort of is clear, okay? But if you want to be rigorous, and you want to keep writing long equations, this is the correct notation, but just P of x is good enough. All right, definition now of something hopefully you know, the cumulative density function. And so the cumulative density function for a random variable x is a function f of x that returns the probability that capital X is less than little x. So effectively, the cumulative density function is nothing else but an integral of the density function integrated from minus infinity to z. Okay? So, so this gives you the probability that x will be less than z. Okay? And this is a definition of the cumulative function. If you want to see this in action, and I'm sure you have used this as an undergraduate, if you know the cumulative function and you want to find the probability that you will be between a and b, effectively this is this integral, right, where this is the density function, and this integral using this definition is nothing else but the CDF computed at b minus the CDF compute.a. Okay? Just a definition again, this doesn't add anything new, but obviously definitions are introduced because often they make algebra easy. All right, so let me bombard you with things you need to know, so I'm going to put all of these things up. So we talk about a random variable x. The expectation or the mean value of x is defined from this integral, x times p of x dx. We define the variance of x as the expectation of x minus e of x squared. Often, if you expand this, this is the expectation of x squared minus the expectation of x squared. And the square root of that is the standard deviation of x. Okay? And again, these definitions, the way I have them, are for scalar variables. And I think somewhere down the road, we will extend this to vector random variables as well. All right, so if instead of x, you have some function of x, you can use the same definition. So the expectation of any function of x is basically t of x times p of x dx. And the same thing about the variance. So the equations look the same. So this is very useful. You can put any sort of function of the random variable there. Obviously, if x is a random variable, t of x is a random variable, right? So the same definitions as before. Now, what is useful in practical calculations is to compute moments beyond the mean and the variance, and those moments defined here. So x minus the mean of x, the power k. If k equals 3, this is the skewness of the distribution. If k is equal 4, this is the kurtosis. Almost most engineers never bother to use this, but you know, if you play with distributions that they are not Gaussian, people will ask you, if you do some Gaussian approximations, they will tell you, well, you know what, go and compute these moments and tell me, is this really a Gaussian? Okay? So if you want to see how much you deviate from the Gaussian distribution, you need to report really these moments for k equal 3 and k equal to 4. And most people who do these calculations, they realize obviously it's easy to get the mean, it's easy to get the variance. As you go to higher moments and you want to compute these integrals, it becomes a little bit more tricky to do these calculations correctly. So for example, one method may give you excellent answers for the first two calculations, but you may have a hard time to calculate higher order moments. All right. I wrote all of these things for, the general case, basically, but you can think of these integrals for the expectations in the case of discrete variables. Instead of integrals, you have a summation in x for all possible values of x. But more importantly, what I'm interested to tell you is this definition of expectations, you can also extend it to conditional expectations. And I will very, very often use in this course some formulas that otherwise will look very complicated for conditional expectations. So I want you to know what the definition is. So here I have a function. The notation is very tricky, right? And sometimes it's being abused when you write papers or you see these things in the book. So here is the conditional expectation of some f given y. Here the idea is, because you see an x there, f is a function of x. Okay? You can write it explicitly, but the fact that you have an expectation with this subscript x here immediately implies that basically the f is a function of x and you take expectation with respect to x, but this is conditional on y. So what is different from this definition? Well, here we had p of x, here we have p of x given y. That's all. Okay? So effectively, the only thing that changed in the definition is that you're taking expectations of a function of x, but with respect to the conditional distribution of p of x given y. And again, you may have lots of conditions, things in your equations, but at the end of the day, when you do the sum and product rules, you know, if you have lots of conditions, cover them up when you do applications of the sum and product rule, and then put the condition there, okay? It adds to the equations, makes them look complicated, but don't omit the condition because the equations may not be applicable without the condition there. Okay, you need to have this condition when we do calculations. All right, so I'm going to do an example of calculating expectations, and let's so we consider the sample space basically to be -1 to 1. So really the events are, you can think of drawing from this line from -1 to 1, okay? And I'm going to assume that the probability measure that I have is uniform, right? So my density function is basically uniform because it needs to be normalized in that sample space from -1 to 1. The density is, P of x is basically 1/2, okay? Can you see that the probability here is 1/2? Because 1/2 times 2 has to be equal to 1. It's uniform, it has to be normalized. You remember when you take P of x and you integrate for all possible values, right? You should get 1. So the space here is 2, of size 2. So, and I am telling you that the probability is uniform, so the probability density is 1/2, okay? All right, so let me consider the following two examples. I define one random variable x1 and another x2, just so I can make the point. And you remember these random functions map the sample space, which is -1 to 1 to the real line, -1 to 1 to the real line, and I define x1 of omega to be equal to 1 for all omegas, all right? And I define x2 of omega to be equal to 2 when omega is positive, 0 when omega is negative. So what I want you to tell me is what is the mean value of x1 and what's the mean value of x2 without putting up the calculations. So you can do the little calculation in your head if you need to, on your piece of paper, but tell me what is the expectation of x1 and what's the expected value of x2. You remember the expectation is x times p of x dx, and you integrate, right, over x. So if you take x1 equal to 1, how much is p of x again on this problem? 1/2, all right? And x goes from -1 to 1, right? So, so what will this give you? So 1 times 1/2 integrated from -1 to 1 is 2. So what happens to the 2's? Cancel out. So obviously for this case, the expected value is 1, which makes sense, right? Okay? What is the expected value of x2? Do the calculation for me. Notice that x2, the way I define it, is 0, where omega is less than 0. So when you calculate the expectation, obviously you're going to have to integrate from 0 to 1, not from -1 to 1. From 0 to 1. So what result will you get? We'll get 2 times 1/2, which is 1, integrated on what? From 0 to 1, which gives you 1. So what's the value? 1. But this function never takes the value 1. Message here, don't, expect that the expectation of the function, right, or the random variable, needs to coincide with any of the values this random variable can take. In this case, the random variable can take only values 2, but the mean value is 1. Okay? And even actually more weird, actually I don't know if it's weird, I see the statement here on the bottom, the probability of x can be greater than 1. The only constraint is when I integrate this p of x over this sample space, basically I should get, as a result, 1, but at any given point, p of x can be greater than 1, okay? So, and a typical example is, if you have a uniform distribution from 0 to 1/2, because this needs to integrate to 1, this probability density of this uniform distribution has to be equal to 2, right? 2 times 1/2 gives you 1. all right? So 2 is greater than 1. So if you see probability as being greater than 1, probability, the values of this density being greater than 1, don't be alerted, because you say, but how is it possible probability is supposed to be sum to 1? Well, this is the density. It's the integral of this that needs to be 1. Okay? All right? Later on, we may even see some densities that go to infinity. For example, we have singularities and things like that. Okay, so what I'm going to do for the rest of the lecture, I'm going to bombard you with some trivial distributions that you are familiar, but I'm trying each of these distributions to bring concepts from later on in the course, so you start seeing things that we will formally introduce way later in the course, okay? So that way, if you get bored listening to trivial things, I will try to throw you out of your chairs hearing something you don't know. So this is the uniform distribution from A to B, and you know, so this distribution is basically non-zero only from A to B, and what the notation here is, this is the indicator function. I already have introduced this earlier. The indicator function, it is 1 when x is, you know, in this case, when this is true. All right, so when x is between A and B, this is 1, and the density is 1 over B minus A. Indicator functions will be used everywhere in statistics, okay? So if the argument is true, then this is 1, right? So think of a distribution from A to B that is uniform. It has to be 1 over B minus A, because when I integrate it from A to B, I need to get equal to 1. All right, so that's the definition of the uniform distribution. So this is the CDF. It's basically 0 for x less than 0. It's x from 0 to 1 and 1 after that. And these are the values for the mean, the second moment, and the variance. What I would suggest is, don't memorize things, but when you start using these things, you know, they will be coming often to your heads, because these are calculations you will need as intermediate steps in other more complex calculations. What I suggest is, when you want to look for, let's say, something about the uniform distribution, what I do is I go Wikipedia uniform, and there is everything with all the formulas. So don't memorize things. Know where to find them. Okay? Of course, you need to know what a uniform distribution is. Okay? You know, if this was an undergraduate course, everybody would memorize all these formulas and do algebra with these formulas. We're not going to do this. We're, you know, we will let the computer do these things for us. All right. Trivial extension now to this a Gaussian distribution. I say that the random variable x is a Gaussian. So this is a univariate distribution with parameters mu and sigma square, when the probability of x is less than equal to t is equal, given by this nice formula. So basically, this is the density of the Gaussian. In life, everything is about the Gaussian. And it sounds like, yeah, that's trivial, you know, last century type of calculations. Fortunately, every complex calculation at the end of the day starts and ends with a Gaussian. Okay? So you need to know things up and down, left and right. Unfortunately, not with the univariate Gaussian. You need to know things with the multivariate Gaussian. And I'm going to give you some headaches when we reach those lectures. Because the formulas are universal, but sort of they look a little bit complicated. But we need to start with the univariate Gaussian. So you can actually prove. The proofs are in the notes. They don't take any time. Some simple integral calculations. You can prove that this parameter mu is the mean of the Gaussian, and sigma squared is the variance. So if you take the definitions of the mean and the variance that I gave you, you can show with some algebra that mu and sigma squared are indeed the mean and the variance. You can actually show, and the proof is in the notes. Somebody will say, well, you know, how do you know that this is normalized? How do you know that the integral of this is to 1? Well, you know what? Because when I want to convince myself that I know what's going on when I start teaching, you know, if you do the algebra, 3 steps there, I'm not going to go through. just using some polar coordinates to transform integrals from Cartesians to polar coordinates. In 2 lines, you can show actually that this is a normalized distribution. Again, should you actually bother and look at this? You know what, if you have time, do, because there's always something to learn. Because, you know, if you know how to manipulate Gaussians, nothing will scare you when you read textbooks and papers, right? So the calculation is simple. Okay, the proofs, again, that the expectation and the moments, you know, are there. The only thing you need to do is you need to know integrals, and I give you what the integrals that they're coming in these calculations, they're given like that. Again, you may want to, you don't really need to prove anything because the proofs are in the notes, but read the proofs so that you know that nothing comes out of nowhere. A very important note, in machine learning, many times, rather than working with the variance sigma squared, we work with what's called the precision, which is 1 over sigma squared. And the notation for that is lambda. So often we're going to see the Gaussian written in terms of precision, okay? That's an information theoretic way of writing the Gaussian, and it's going to come very handy when we try to generalize, different families of distribution. So lambda would be used as the precision of the Gaussian, which means, you know, a Gaussian basically that very high precision would be very narrow, okay, like a delta function, okay. So the higher the lambda, the smaller the sigma squared, and more narrow this Gaussian becomes. Okay. You see here, this is when the mean is 0 and the variance is 1. This is what is called the standard normal distribution, N0, 1. And usually, if you take an undergraduate book or some, you do some applied statistics in various courses, you usually, if you want to calculate things for any other Gaussian, effectively you have to use the tables of the standard normal, all right? And I give you the derivations actually that you need in the next 2 slides, but really it's a basic type of calculations. If you want, for example, if you have a Gaussian with mean mu and variance sigma squared, and you want to find the CDF at a given location x, which means the probability of x being less than little x, really what you have to do is take the CDF of the normal standard Gaussian and compute that at x minus mu over sigma. Okay, and really the algebra is it's on those 2 slides. So so when you see statistics books and they have tables of this, the CDF of the standard normal, it's because those tables, with some simple transformation here, you can use them to calculate probabilities for any other Gaussian with any arbitrary mu and sigma squared. All right. Now, what are the bad things about Gaussians, okay? And and again, don't get me wrong, we're going to do lots of things about Gaussians because even the most advanced methods in machine learning today, they try to force things to be Gaussian because if they're Gaussian, everything becomes trivial, okay? So very advanced methods, are trying sort of to force very complicated distributions to become Gaussian, or some, because if they are sort of mixtures of Gaussians, then they are getting very complicated. But there are problems, all right? So you see here a nice Gaussian. It's symmetric, okay? And the second also very important thing is you notice it goes down exponentially to 0 tails. So it has no fat tails. And not having fat tails has a lot of implications in what? Anybody knows? So if you try to do it, and possibly we will give you homework on this, right? So if you try to fit data to a Gaussian, and you have some outliers, data that actually they are wrong data, they don't come from that Gaussian, the calculations, the Gaussian you will get, it will be completely messed up, will be completely unreal. So a Gaussian would not be robust, basically, to outliers. If some data point is the wrong point, it came there by accident, and you try to fit all the data to a Gaussian, you're going to get a problem. And that has to do with not having fat tails. Okay, so there's no skewness, of course, and obviously it's a single mode. Okay, I mean lots of things in physics, chemistry, biology. The multi-models, there are different sort of modes, of different structures or different equilibrium states. They cannot be represented with a Gaussian. Okay, you can try to smooth them, but basically that is not the case. So why we bother with Gaussians? It's a very easygoing distribution. It's defined with only two parameters, mean and the variance. And we will see this formally. We will spend a lecture basically to discuss about this. There is the so-called central limit theorem that says if you take samples independently from any distribution, all right, from any distribution, their sum follows a Gaussian distribution. An amazing theorem. So take samples from any distribution all right? Add them up and repeat the experiment. The sum that you'll be getting will follow a Gaussian distribution. And that's why when we discuss about noise in different Bayesian models, we take the noise to be Gaussian because it's really the summation of IID random variables coming from whatever that together effectively they give us a Gaussian distribution. Now there is another important reason why the Gaussian distribution is important. The Gaussian distribution is what we will learn later on. It's a maximum entropy distribution. So let me tell you with words what that means. If I ask you, find me a distribution that has this mean, this variance, and beyond that is as random, it gives you the extreme randomness that you can get on Earth. Okay, but I fix you this mean and this variance. You know what distribution is going to come up when you do the calculation? The Gaussian. Okay, and that has lots of implications. So it's a maximum entropy. We will define entropy later on. But right now, if you fix the two parameters, right, and the mean and the variance, and you try to maximize the entropy, you will get a Gaussian distribution. All right, so I'm going to bypass this, okay? And I have, just for your information, there are always little programs. For example, if you click this, and assuming that the click works, if not, you have to let me know. It uses some data, all right? And then it's trying to fit a Gaussian, okay? Now, I really haven't said how to fit this to a Gaussian. To fit to a Gaussian, you need to know what the mean and the variance is going to be, and for that, you're required to know some estimators of the mean and the variance. So I haven't done that yet, okay? So for those who already know, this type of calculations on this and the following slide, they use what's called the maximum likelihood estimator. But we will formally do this, we'll spend lectures on that topic. So I can tell you, so if you are curious, and how is this maximum likelihood estimators for the mean and the variance look like if I give you data and you try to fit a Gaussian? Well, think of them being sort of the sample mean and the sample variance, if that resonates. So if I give you data and you can calculate for me the sample mean and the sample variance, well, literally those things come to be the maximum likelihood estimator. So what we do here is we compute the sample mean and variance, and then we plot a Gaussian. You can see this looks nice. Here is even another example with more complicated data coming from an image, and you fit them because you have lots of pixels here to fit in. The distribution looks even better. If nothing else, look at the slides to see how you plot a Gaussian with in MATLAB, because if you know how to plot a Gaussian, it will be useful information for your homework later on. So this is a good time to do that. All right. All right, so let me very briefly discuss about quantiles, and you're going to have to do some calculations of this to post-process your results. So this is the definition of the CDF that we discussed it. So the CDF compute at x0 is the integral from minus infinity to x0 of the density dx. Okay? Definition. We define the value y with parameter alpha to be the alpha quantile of the distribution with CDFF when f computed at this y alpha is equal to alpha. So you can, for example, think if you want to define the median, then you will set alpha equal to 0.5, and what we're interested is, we're interested on this value y for which the CDF gives you value 0.5. So you're looking basically at the point where to the left you have 50% of the probability mass, all right? So this is a useful practical calculation, especially for those who play with real data. Now, a warning, when we become Bayesian in a few lectures, this type of quantiles will be a little bit different in the Bayesian context. Okay, so what I'm discussing here are very general ideas, but later on we will do things a little bit differently. Okay, and also, let me put all of these things up. You can also define the tail probabilities. So if you set, let's say, alpha equal to 0.05, and you want to define the location where the probability up to that point is alpha over 2, and similarly here the probability after this point being also alpha over 2, you can compute these two locations that you see there, and you can compute them. This is for the standard normal. The location is take the CDF, invert it, and compute at alpha over 2, and here take the CDF and compute it. If this is alpha over 2, right, this location would be 1 minus alpha over 2, okay? And these 2 points come to be minus 1.96 and 1.96 for, again, for this standard normal. And for an arbitrary Gaussian, the points basically that contain 95% of the probability mass are really the mean minus 1.96 of the standard deviation and the mean plus 1.96 of the standard deviation, and we usually approximate this as mu plus minus 2. Okay, so I don't want again to spend time on things that I hope you have seen. And again, if they come somewhere in the homework and you forgot because I went rapidly through this, if you search on the web, you will, or in the slides, you will come up on the slide and everything you need to know is here, okay? So again, central interval contains from minus 1.96 to 196 contains 95% of the probability, okay? And mu plus minus to sigma if you want to generalize this for any Gaussian, okay? Again, and all of these are for univariate Gaussian, so we are talking about scalar variables. All right, how you are going to do this in 50 variables or anything like that, we will be dealing on it later on. Okay, we have 17 minutes, so I have time to discuss other random variables. Usually, like last year, I don't believe I covered these topics. I said to the students, go and read them. Okay, so I'm going to go slow and try to cover them and bring some concepts here and there. But, you know, we're going to have to accelerate somewhere else. Or we're going to have to miss some other topics. Okay? So there is a merit to see these distributions, first because I'm going to be using them, and secondly because the notation and some of the calculations will be actually calculations we will need to generalize to complicated scenarios. So let's discuss this concept of binary variables. You may say, who cares about binary variables? These are distributions that at the end of the day will be coming up out of nowhere in more complicated problems, okay? It's not like we're really interested on a problem on a binary variable and that's it, right? We're interested in something else and somehow, somewhere in the process, a binary variable calculation is coming through. So let's think of a binary experiment, heads equal to 1, tails equal to 0, and we define mu to be the probability that I get heads, and 1 minus mu, the probability that I get tails. So this is the Bernoulli distribution that is written. The distribution computed at little x is mu to the x, 1 minus mu to 1 minus x. Think again that x can take the value 1 or 0. If it takes the value 1, this is equal to 1, so you get mu there. If x equal to 0, right, this is 1 minus mu, and this is 1. Okay? Talking about learning something, right, from doing the slides, this is not a very good way to write these binary distributions. This is the right way to write on the bottom, and maybe you have not seen that one. Because it tells you everything you need to know. So here you have to, when you write this, in your top of your head, you have to say, yes, but x equal 1 or 0. Well, this is written explicitly here. It says this Bernoulli distribution computed x is mu to the indicator function of x equal to 1 times 1 minus mu, the indicator function x equal to 0. So when is this term non-zero? When x equal to 1. And the indicator function is 1. So when x equal to 1, this is 1, so you get mu. Then this would be wrong, you get 1. Okay, this would be 1 minus mu to the power 0, and the other way around. So this is really the proper way of writing these binary variables using indicator functions. So if you use the definition of the expectation and the variance, it's very easy, right? Because this is a discrete variable. You have to integrate some, basically, for the values of x being 0 and 1, and immediately you will see that the mean is equal to mu, and the variance is equal to mu times 1 minus mu. And actually, try to remember this calculation because you're becoming so often, and so it's going to be very valuable. So the expectation is mu, and the variance is mu times 1 minus mu. I have not really defined, well, the definition is actually here. That's why I put the definition symbol here. But this is the entropy. This is the definition. Okay, I'm just giving you this definition so you know, if you ever look again on this slide, to have the entropy calculation as well given for you. Okay. So the entropy, the way I defined here, is p times log of p, sum for all possible values of x, and you get minus mu log of mu minus 1 minus mu log of 1 minus mu. Okay? But right now, what we're interested in is that the mean is mu and the variance mu 1 minus mu. Okay. I said we will use this basic slide so I can still start introducing concepts that we will formally discuss later in the course. Okay? So I want to use this slide to define what is called the likelihood function for the Bernoulli distribution. Okay? So we will see something that is going to be formally introduced when we start talking about Bayesian things. So what's the likelihood? You remember in this binary distribution, we were doing an experiment with the coin heads or tails. Okay? So suppose that you repeat this experiment n times, and the first time you collect x1, then x2, then xn. So x1 to xn can be 0 or 1, but these are your data. All right? These are your data. So the major assumption in calculating the likelihood that we will make in this course and every other course is that these events, x1, x2, xn, these values that we got, given the parameters of the distribution, are independent of each other. This is very important. So if you want to calculate the probability that you will actually observe x1, x2, xn, these are the data d, given mu, this is actually nothing else but the product of the probability of xn given mu for all n. So effectively, what rule of probability do we use to write this calculation where d is that? What is the rule of probability that we write there? It's not actually the rule, it's a definition of probabilities that we introduce. Independence, all right? You remember we said the two events are independent when the probability of x and y is probability of x times y. So here, d consists of x1, x2, xn. So the product of this will actually define me the likelihood. What is important, okay, very important, you notice is given the parameters. This is extremely important. So if you knew the parameters, then you can use this independent relation. So let's see how the formula goes. We have product over n. This is my Bernoulli distribution, right? And instead of x, I put xn for each of my experiments. I call the value of x xn, okay? And what have I done from here to there, guys? Can you tell me what is m now? There is product of all of these things, and now somehow I see the product has disappeared. What have I done? I'm going to have a lot of terms like this here, mu to x1 times mu of x2 times mu of x3. So what is m? Huh? It's, in the particular case, since we talk about heads and tails, oh, it's there. So it's the number of times we will get heads. Right? You see that? Because if I sum x1 and x2 and xn, and each of them can take the values 0 or 1, right? I'm going to get how many times I got heads. Okay. So effectively, you know what? This little m is called the sufficient statistic. So I can introduce you to new names here. And it is the sufficient statistic means you don't really need to know all the details of the data. You only need to know m to compute what? I mean, when you calculate the likelihood, before I said something about maximum likelihood, we will talk later, but somehow we talk now. What will be actually something that someone will be interested? If you do these experiments, what will you be interested actually to compute if you try to fit this with a Bernoulli distribution? How about the mean of the Bernoulli distribution? Okay, so m is the sufficient statistic actually to compute the parameters of the distribution. So you don't really need to know every single detail of the data. You actually need to know the sum of x1 plus x2 xn, which is this number n. If you know m, that defines the parameters to your problem, if you do a maximum likelihood estimation. And I do believe on the next slide, do I? No. So it's maybe somewhere in another distribution. So if you wanted to calculate an estimate of mu, what you can do is take this and consider it as a function of mu, and take the derivatives equal to 0, and then compute mu, and that will be your maximum likelihood estimate. Okay? I will give you some examples as we go later on. And again, I am throwing things here that we will formally see 2 weeks, 3 weeks down the road, but you know, you don't want me to bombard you lecturing about Bernoulli distribution and say I'm not interested in this course, so there it is. Okay? All right. Binomial distribution. It looks like the Bernoulli distribution. What's the difference? So I am counting how many times on my coin experiment I get heads. The difference from before is, before you do only one experiment. You take the coin, you throw it, heads or tails. Here you do the experiment how many times? N. And you're asking in this n times, how many times did you get heads? But you're not, you have to put this normalization factor, because if I tell you we're going to get heads, let's say, in an experiment of 3 trials twice, well, you may say, do you get heads the first time and the second, but not the third, or you get the first and the third, but not the second? So this factor here accounts for all possible ways of getting heads in that experiment. It's nothing but a normalization factor. So this is a generalization of the Bernoulli distribution. It tells you if you do experiments and trials with a mean, the probability of getting heads in each time being mu, the probability that in the n experiments you will get m times heads is given by this nice equation. It's really the probability of this little m that we showed before, okay, of the times that we get heads. And here you see a nice plot. Again, there is a MATLAB code. In this case, mu is equal to a quarter and n equal to 10, okay? And that's the binomial distribution. And there's another plot there. All right. Again, I may give you, I'm not going to give you homework, so you have to do things by You know, I said I'm not going to give you homework. I told my TAs, I don't want to see the homework. You take full responsibility. Okay? So they will give you whatever they want to, and because they suffered last year, I don't trust them. Okay? They're going to try to take revenge. They say if we went through this, we have to make the students this year to suffer as well. But a calculation they may ask you is, okay, for the Bernoulli distribution, we know the mean is mu, the variance is mu minus 1 minus mu. If we know this for the Bernoulli distribution, how do we calculate actually the mean and the variance of the binomial distribution? Can we do any trick that somehow will allow us to calculate the mean and the variance of the binomial distribution without doing all these big summations and complicated calculations for the binomial? And here's the trick, okay? I want you to read it, okay? You remember in the binomial what we do is we do n experiments. And m is really x1 plus xn, isn't it? I mean, if x1 is heads and the other one stays, I'm counting 1, 0 plus 1 plus 0, 0 plus 1, etc. That's m. So really, m is the sum of n random variables that they're actually independent, and these random variables come from what distribution? From the Bernoulli. So, because they're independent, the mean of this and the variance of m is really the summation of the means of these x's, which are Bernoulli variables, and the variances of these x's that they're Bernoulli variables. So effectively, in one line, the mean of m is really n times the mean of the x's, which is mu, and the variance is n times the variance of the x's, which is mu1 minus mu. If you want to do the algebra, you can do it. It will take you one page. Here with some reasoning, you can get the mean and the variance. And actually, here's the lecture proof, okay? And actually, here's also the proof that, that the Bernoulli distribution is normalized. If you don't want to read it, don't read it. If you like to keep yourselves busy, do that, okay? So let me generalize now. We have 3 minutes, okay? Let me generalize the Bernoulli distribution. This will be extremely important in the context of machine learning. So we're going to assume, rather than having a binary variable, we're going to assume that we have a k-dimensional variable, all right? And in every experiment we do, only one of these k elements of this vector x will take the value 1. Everything else will be 0. So this is 1 in k setting, all right? So you have a vector, okay? And only one of its elements will take the value 1. Everything else will be 0. And what is the probability in a single experiment that this will take the value 1 is mu k. So two things happen. If this is x, the sum of all the components of x will have to be equal to 1, because only 1 takes the value 1. And then the sum of all the probabilities of having 1 here or 1 there has to be equal to 1. Both of them simultaneously. Okay? So what is the probability of this generalization of the Bernoulli distribution? It's very simple. It's given here. X here is a vector, mu is a vector. So I have k states, and the probability of hitting, let's say, heads on state 1 is mu1. And you notice the notation I use here, mu k to xk. If xk happens to be 1, then I get mu k. If it is 0, then I get 1. I get no contribution, all right? And if you wanted to make it really nice, the product of over all the states of mu k times, exponent, the indicator of xk equal to 1. So if xk equal to 1, this is 1, and then you get mu k, okay? So this is, again, a generalization of the Bernoulli distribution, and it's going to be extremely useful actually in various contexts in the course and in many other related courses. Okay? So you can actually show that the distribution that I just showed you is normalized, and easily the mean comes to be equal to mu, to the vector mu1 to mu k. And this distribution goes with different names. Categorical distribution is what people in machine learning use. multi-nully distribution is what others will use. Do not confuse it with the multinomial distribution. Anybody knows what is the multinomial distribution? So this is the multi-null. I mean, I don't know who introduced the names. You see it in machine learning here. I don't know what statisticians use. Categorical is most probably what you see in statistics. But what is, before, you remember we had the binomial, and then, we had, we started with binary variables, and then we went to the Bernoulli distributions with n trials. Can you think what's a multinomial distribution for this k-vector setting? In the k setting, what we did is we did one experiment, and we say, what bin are we going to hit, right? xk equal to 1, let's say, with probability mu k. The multinomial distribution is nothing else but extending this to n trials of the experiment. So you do these n tries. The first time you go here, the second there, then there, etc. And then, so the multinomial distribution looks like the multi-nully. The only difference, you know what it is the normalization factor that you have to put on the front, okay? Where, what do you think M1 is going to be? The number of times that you hit, k equal to 1, and 2 the times you hit k equal to 2, and then actually this should be capital K, all right? The number of times you hit capital K. I think it's 1:46. We can call it a day for today. There will be a very short lecture tomorrow, so we can finish these things, okay? So I will see you tomorrow. And if anybody has any questions, you can see me tomorrow after lecture, because I'm going to have office hours on Fridays. And also you can email me, and I will try to do my best to answer any questions, okay? So I'll see you tomorrow.